Our talk today is Graphic Content Ahead towards Mobile Automated Scalable Analysis of Graphical Images. And our speaker is Alex Long. Thank you.
Thank you. Thanks everybody for coming. Glad you could make it. I'm going to be talking about some work. I'm Alex Long. I'm going to be talking about some work done by myself, Joshua Sachs, who's in the audience and gave a talk earlier, Robert Gove, and David Slater of Invincia Labs on a automated scalable approach to analyzing images extracted from malware. And I know many of you may have come, tempted by the graphic content title, but I do have to warn you, this next image had to have parts of it blocked out in order to be able to show it to you today. I'm going to be talking about kind of the status quo of malware analysis research and an opportunity for image analysis left by this research, and our method for comparing images in an automated way. And then 2 research experiments we did exploring how computer vision and machine learning can be applied to this problem to do it in an automated and scalable fashion. So our story begins with a malware sample. That's this guy. And a lot of work has gone into researching various techniques for analyzing samples like him, such as various static analysis techniques like concolic execution or tainted information flow, and various dynamic analysis techniques such as simulating user actions to execute various code paths or capturing code that gets generated or unpacked at runtime. But these techniques focus almost exclusively on the code of the malware and the the resources of the malware, which can include things like natural language, documents, audio files, video, and images, tends to get pretty much dropped on the floor and left out of the research completely. And while a lot of time and money has gone into these research techniques, malware authors are working hard too. And they're doing things like packing their code, including dummy code as a red herring, or building in anti-debugging and anti-VM functionality so their code stays inactive under analysis. We believe these resources are a valuable alternative signal when combined with more conventional kind of research techniques. We stand a better chance of getting around some of these obstacles that malware authors are throwing up. In a collection of 1.5 million malware samples that we had in our lab, we found that over half of them had at least one image embedded in them, like the ones you see here, and many had more than that. So this is where we chose to focus our research, and not only because of the prevalence of images in malware, but also because images play a special role in the way that malware tries to manipulate the user. After all, a packed VM detecting Trojan still needs an attractive or trustworthy icon to get the user to click it. Of course, looking at the resources in malware is standard operating procedure for doing manual analysis. By kind of automating the process, we can do this at scale over hundreds of thousands of malware samples. And this opens the doors to being able to do things like search across millions of malware samples for similar images, or compare the semantics of an image with other things that we know about it. So if we know we have this file and we know it's a PE binary, but we also detect it has a Windows folder icon, that's kind of strange. But before I get into that, I'm just going to talk a little bit about how we did the comparison of images in malware. As we were working through them, we quickly found that one does not simply compare the images extracted from malware. Trying to do things as simple as MD5 hash matching tends not to work because images get changed in compression, the resolution gets distorted, and they can also be changed deliberately by attackers trying to evade such a technique. So the algorithm we used is called average hash, and it's a very simple kind of algorithm computationally, which is good because we're running this across thousands of samples. And just to walk you guys through it, you start with an icon like this PDF icon. You reduce it to grayscale, and then you stretch or shrink it to a 32 by 32 pixel resolution. And then you convert it to high contrast. So in order to do this, you get the average value of all the pixels, which is just some value between 0 and 255, depending on how what shade of gray it is for each pixel. Add all that up, divide by the total number of pixels, pretty elementary. And then for each pixel, if it's above that average, we set it to 255. So if, in this example, the light gray pixel becomes white, and if it's below the average or equal to it, then we set it to 0. So we make the dark gray pixel black. What you end up with is this monochromatic masterpiece, which is a pretty far cry from the image we started with, but this is actually good for us because even if we start with this crummy low-res version, that's all blurry and kind of distorted, we end up with a relatively similar representation in average hash. And this is ideal for trying to apply things like machine learning. You need it all to be kind of in the same representation. We evaluated average hash compared to MD5. So to do this, we hand clustered 200 malware samples in terms of whether or not they had similar images. And we found that MD5 had better precision, which means basically it got less things wrong. But average hash had better recall, which means it got more things right. And that may be a little confusing if your statistics are rusty. Just to walk you through it, if we had a malware sample, suppose this box represents a malware sample, and these images were extracted from it, average hash might detect these other malware samples as having similar images. And this is relatively good. The exact match in the top left, it got. It also got these kind of distorted, degraded versions in the bottom right. But it got a false positive. It got these question marks, which we don't want. That's not a correct match. But the false positive is actually kind of tolerable because to a human, it's relatively obvious that that's incorrect and you can kind of visually ignore that. The alternative, if we were to look at MD5, MD5 wouldn't get that false positive, so good for MD5. But MD5 also wouldn't get the degraded kind of near duplicate. It would only get that exact match. And the near duplicates are really kind of what we're trying to get at here. So we favor the kind of flexibility of average hash, even if it leads to some false positives. So for our first experiment, we looked at how we could detect and visualize these relationships between malware samples. And kind of the idea here is if you could explore a malware sample's social network through these shared images, maybe rare images, like in this example, this kind of gun thing, you can kind of begin to identify, first, is it even malicious? And then you can apply the results of your analysis on other samples to this kind of unknown sample. So if we know nothing else about this unknown sample here, we can see that it's sharing an image with two samples we've previously analyzed and identified as being Trojans. The problem's a little bit more complex than just comparing two images, though, because we're actually comparing sets of images in malware samples. So we want to recognize when there's a missing image in one of the sets. So the formula we use is the number of matching pairs, which in this example is 2, divided by the number of possible matching pairs, which in this example is 3, which gives us a 0.67 similarity score in this example. So we're kind of penalizing the score here because sample A isn't providing a partner kitty to that poor lonely kitty in sample B. And that's just intolerable. So to show you guys how this plays out, perfect. Okay, so let's see. All right, this is a good example. Just to explain the interface here, these text items on the left side are various malware samples we had in our collection, and then when I clicked on one, it searches our database for any samples that share images with that one. And so this image with so each box is a malware sample, and the images in the box are images we extracted from it. And the box with the black kind of thick border is the one that I clicked on. So you can kind of see the scoring algorithm playing out here. So you can see it has the Windows installer icon, which is shared with this other malware sample. But the score, as you can see right here, is 0.25 because it only has one of the 4 images. So that's kind of a pretty straightforward example. Let's do something a little bit more interesting. So in this example, the sample I clicked on is, again, the one with the thick black border. And this is actually a really good example of kind of in an operational context. If you were an analyst and you had 1,000 samples dropped on your desk and you have to analyze these, and maybe they're heavily obfuscated or packed or something like that, a quick way that you could kind of get a sense of them is to throw them into a system like this. And so in this example, so something I forgot to say, the text labels above the boxes are actually generated by AV engines. So if it says Trojan, that was detected as being a Trojan by antivirus. But in this example, we have an ABC053, that's the hash of it, because antivirus wasn't able to detect it as being malware. So we can see, although we don't know that it's malware, we can see that it's sharing this kind of strange 7 image with something that was detected as being a Trojan. So knowing nothing else about it, we can at least see there's something suspicious going on here. And it's also sharing this 7 image with this other malware sample that has these other icons in it. And something else we added to this, kind of in the idea of 6 degrees of separation from Kevin Bacon, is we added the 2nd degree of separation from the sample that you click on. So these other samples that you see kind of drifting to the left and the bottom, they don't share that 7 image with the image that I clicked on, but they do have, let's see, they do have these kind of like green checkboxes and red X's, kind of like interface icons, which are also in this sample, which has the 7 icon. And this kind of allows you to explore the context that a sample is found in. So you can imagine even if antivirus hadn't labeled this sample in the center or the sample to the right as being Trojans, we could still get some sense that, hey, there's something suspicious going on here by the fact that, okay, here something was identified as being a Trojan, here as well. So this just kind of allows you to kind of broaden your general awareness of the context for that malware sample. All right. So the second experiment we did was in the automatic classification of images. So that's basically what does the image look like? So in this example, we have the Windows system icon or Windows folder, pornographic images or game-related. And the idea here is, as I said before, if you identify something as a Windows folder icon and it's an executable, for example, that would be kind of suspicious. Also, if someone just downloads something with a pornographic image or a game in their office, that's probably risky, probably not something we want to allow. And so by being able to automatically detect that, we can kind of just cut it off, block it right there, or at least alert that to security. So how do you solve a problem like automated malware image classification? I'm glad you guys asked. By the way, this is about as graphic as this presentation gets, so hope you guys enjoy. The way we did it is we used Google image search results. So we basically had a different key term for all the different categories we wanted to capture. So in this example, I searched for Internet Explorer, and I get mostly Internet Explorer icons with a couple My Little Pony icons, which we aren't going to worry about. But the idea here is if you have a category game-related, pornographic, you can plug that in to something like Google Image and get a bunch of kind of training data for that category. So you get a bunch of examples of the category that you're looking for. And then you can begin to do matching with the images found in malware. So the way we did that matching was using machine learning. We used a variety of different techniques. I'm going to walk you guys through a super simple algorithm known as k-nearest neighbors, just to give you kind of the intuition behind it. And this is kind of a textbook example, just to get the idea. So if you imagine a graph where the x-axis is the number of rooms and the y-axis is the square footage in somebody's home, and then you went around, you asked a bunch of people, okay, how many rooms are in your home, what's the square footage, and do you live in an apartment or a house? and then you graphed those points. Okay, and then you asked somebody the number of rooms and square footage, and they told you, but for some reason they were really paranoid and they didn't want you to know if they lived in a house or an apartment. That's not the most relevant example, but the idea here would be that you would pick the k nearest neighbors, where k is just some integer as appropriate for your data. So in this example, I picked 3. And so you look at the 3 nearest neighbors, and you just take the majority vote. So we have 2 houses and 1 apartment, so we figured out Mr. Paranoid lives in a house, and he's not very happy about that. So applying that to our problem, one of the things we tried was kind of classifying images by their color histogram. So that's basically the overall color of the icon. It's a little hard to visualize in a presentation because it's more than 2 dimensions, but if you can imagine kind of a space in which the icons are floating around and sort of clustered, where icons with similar colors are nearer to each other, that's kind of the idea. And then, so we have a bunch of labels for all of these. We know, from our Google image technique, we know what a lot of these are, but we have the icon in the center, the red question mark, we don't know what it is. So let's take the k nearest neighbors. In this example, we take 7, so we find we have 4 flash icons and 3 dialog icons, so this is a flash icon. So that's the basic idea here, and it works reasonably well in this example for flash, and in some other cases, color turns out to be a very distinguishing factor, but not always. In this case, we have this kind of blue, kind of probably antivirus shield, and it's just surrounded by things, all sorts of random things. So it's not really, blue isn't a distinguishing feature in this case. There's been a lot of advancements in using neural networks to kind of identify which features are important. So is it the overall color, is it the shape, those kinds of things, and that's probably what we would be looking at next to kind of hone this experiment to get it to kind of operational levels of accuracy. So in conclusion, the graphic content that we find in malware is really underutilized in research, and it's basically just being left out completely. And by applying computer vision and sprinkling a little bit of that machine learning fairy dust on it, we can make this lost signal exploitable and accessible at a large scale. So that the next time we see this guy, we have a new tool to fight him off with. Thank you. Any questions? Okay, sure. So you asked, is it a public tool? No, the code's not available anywhere. Although I could possibly get it to you. I don't know. This was a research project, so it wasn't something that we actually released. But certainly possible, and I could get your business card afterwards if you're interested. Thank you. Cool. Mm-hmm. Mm-hmm. Yeah, so for average hash, yeah, something I didn't really go into is once you have that black and white version, that's basically a vector of just zeros and ones, right? Zeros for black pixels and whites and ones for white pixels. And then you can just do Hamming distance between the images. So basically, how many bits are different. So that's how we did that. Yeah, in the back.
Did you do any analysis when, like, you showed you found something that you thought because it had a 7-zip icon? Did you do any analysis to actually check if those are malware?
Well, no, we didn't. A lot of these malware samples we got were kind of already, we didn't know a lot about them other than what the antivirus had labeled with them. So that's basically what we worked off with. We trusted that from our source that those were correct, but yeah, that's all I can really say. Thank you. Yep.
Alex, I feel like you should say that in the similarity analysis case, we knew that stuff was malware in advance, right? Because this was more about attribution, right?
Yeah, I mean, Okay, so this is Joshua Sachs, also a member of my team. I mean, we knew it was malware because it was delivered to us, and
yeah, I mean, I'm just saying, like in the similarity case, the detection wasn't the goal, right? And analysis was the goal. Like analyzing the malware once we knew it was malware.
right.
Anyways, it's never mind.
Yeah. Cool. Yes.
Is this detection feature something that you plan to, I guess, maybe implement in the heuristic features of malware detection?
Yeah. Actually, I don't know if you went to Josh's talk, but he introduced Synomics, which was a product that we kind of released into beta and actually worked into our commercial product. So the idea was it could be another kind of tool in the analyst toolbox. So he could use that when he was going through the malware. So that was the idea. It hasn't been integrated yet.
Because the reason I asked that question is because you're kind of opt to kind of give that code out, and I don't know how would your company feel about providing.
Yeah.
I don't know.
You mean how would they feel about distributing like our IP or whatever? Yeah, I don't know. You'd have to talk to the marketing department, I guess. Yes. Yes. Wait, I'm sorry. Did we try using color? Right, yes. Oh, you mean for... Yeah, in general, average hash was working pretty well. So I think that's why we stuck with it for the image sharing work. But yeah, the classification it's definitely like a much harder problem. As I showed you, like even color histogram, doesn't work perfectly. So yeah, we began exploring other techniques for that. Yeah. Yes.
What's the scale of the data sets used with the classification?
So our training sets were actually pretty small. We kind of hand curated the examples, so we didn't have those like My Little Pony pictures messing with our results. So we probably had, 20 to 40 training examples for the different categories. And so yeah, and we were running this process across. I think we had about 400,000 malware samples with images in them. Cool. Thank you. Anybody else? Oh, sorry. Yes. Yeah. We don't, but sorry, I'm not repeating the questions. So she asked, do we take into account the rarity of an image when we're looking at how, kind of using that to look at those image sharing relationships? Yeah, we don't, but that's definitely like a good idea. Like, in like the natural language processing stuff, they do like TDF, IDF to kind of get rid of common words and stuff like that. So that idea would definitely apply. That's definitely something for future research. Cool. Yes.
How long does it take your million samples? How long does it take to run through a million samples?
It's actually pretty fast. We used a library called Flan. I don't know if you've heard of it. The acronym is actually very kind of self-explanatory. It's fast, lightweight, approximate nearest neighbors. So it uses an algorithm that's much more complicated than nearest neighbors to approximate the results, and that way it doesn't have to do like the pairwise comparison, which is part of what makes nearest neighbors very expensive. So using that, we were actually able to do this across hundreds of thousands of samples in relatively small amounts of time. I have 5 minutes left, so any more questions? Yes.
How do you validate that the similarity matching represents similar families
in that's the evaluation that should be done. That we didn't evaluate whether or not the image is really appropriately like clustered. clustered malware. I think our evaluation focused more on just making sure average hash was actually catching similar images. But yeah, that's certainly something to make sure. I mean, that would be one useful application of it. Yeah. Sorry, I'm not repeating the questions again, but hopefully you guys can hear them. Cool. All right, thank you.